Welcome back to part two of chapter 13, now starting buoyancy. So, buoyancy is a force of the water difference. It's the net upwards force due to having greater depth of water at the bottom of the object than at the top of the object. So this feels a little bit counterintuitive, but it's the net upwards force due to being underwater. And you can feel that if you swim underwater, your body is pushed back up to the surface. Um, so what happens here is if you have an object that has thickness to it, the force at either side, the pressure of the water will be the same. That represents my black arrows here. They are the same size, and that means that they're pushing evenly and opposite on either side of the object. However, the top of the object is less deep than the bottom of the object. So the bottom of the object has more water pressure because it's lower than the top of the object does. And that difference between the two of them is called our force of buoyancy. So it's based off of how much space the object takes up that will then push the object up. Now, just because there's a force of buoyancy doesn't mean that the object's actually going to float. Uh, we'll get to that in just a bit. Effectively, the force of buoyancy is equal to the weight of the displaced fluid. So how much water is being pushed out of the way by having the object in there. With that in mind, we want to do a little stop and think. The five blocks have the masses and volumes as they are shown. Use what we've learned and rank in order from least to greatest the buoyant forces on the blocks. Stop, pause, and think about it. Welcome back. So, I know that I'm trying to rank their buoyant forces, and that's going to be based on the weight of the displaced fluid. Now, the amount of fluid that's displaced is based off of the volume of the object. A bigger object by volume will push more water out of the way and displace more fluid. Since all of these objects are fully underwater, they're displacing their entire volumes. The mass of the objects doesn't actually matter. It's just the fact that they are displacing a certain amount of fluid. So it's basically ranking them based on volume from least to greatest. I'm going to start with E because it has the smallest volume. That's going to be less than the three that have the medium volumes, A, which is B, which is C, um, and then the greatest one would be D. And the reason for that, A is not going to have any more volume displaced than B or C just because it's slightly higher in the water. It doesn't have to do with the height of the water or the depth of the water. It just has to do with the volume displaced. Okay, so let's use an equation for buoyancy. The force of buoyancy is equal to the mass of the water or of the fluid times the gravity. Or since I know that the mass is equal to the density times the volume, I can substitute that in for mass, and I can get the force of buoyancy is equal to the density of the fluid times the volume of the fluid times the acceleration due to gravity. This is another one from your AP Physics cheat sheet. That's why I've circled it, squared it, rectangled it in red. Okay, let's do a little example. Legend has it that Archimedes was asked by King Hiero of Syracuse to determine whether a crown was of pure gold or had been unadulterated with a lesser metal by an unscrupulous goldsmith. Ooh, we get to learn about physics and Greek mythologies and legends. It was this problem that led him to the principle that bears his name, the Archimedes principle. In a modern version of his method, a crown weighing 8.3 newtons is suspended underwater from a string. The tension in the string is measured to be 7.81 newtons. Is the crown pure gold? Okay, so I'm going to start with the idea that the crown is hanging by this string. And so I'm going to start with a free body diagram. So I know right off the bat, I have a force of gravity, that would be the weight of the crown. And then going up, I am going to have a force of buoyancy. And then I'm also going to have the string itself, which would be a force of tension. So based on that free body diagram, I know that if I take direction out of the equation, I would have force of gravity equals force of tension plus force of buoyancy. And I have values for those. 8.3 is my force of gravity. So 8.3 newtons equals force of tension, 7.81 newtons, plus the force of buoyancy. And that can give me a force of buoyancy of 0.49 newtons. So I know how much buoyant force there is, but that doesn't actually tell me whether it's gold or not. I do know that the density of gold is 19,300 kilograms per meters cubed. That's given in the little part after the problem. Uh, so I want to compare my density of the crown to the density of gold. And I know that force of buoyancy is equal to, let's reference that equation, the density of the fluid times the volume of the fluid times the acceleration due to gravity. Density of the fluid I have, force of buoyancy I have, so I can plug some of these in, right? No, I want the density of the crown, don't I? Hmm. So I need the density of the crown. In order to do that, the volume displaced has to be based off of the volume of the crown. So I could say that for the crown itself, the force of buoyancy on the crown is equal to the force of gravity, which is equal to the mass of the crown. I'll just call this the force of gravity of the crown, right? The force of gravity of the crown is equal to the mass of the crown times the gravity. I don't know the mass of the crown. I don't know the mass of the crown, but I do know that since I'm looking for a volume of the crown, I could turn that mass into density times volume from over here. Um, so the force of gravity of the crown is equal to the density of the crown times the volume of the crown times the acceleration due to gravity, or solving for the volume of the crown, because the volume of the fluid is equal to the volume of the crown. The volume of the crown is equal to the force of gravity of the crown over the density of the crown times the acceleration due to gravity. Okay. Now, because these two are equal, I can take the volume of the crown, plug it in for the volume of the fluid, because the crown will displace its own volume of fluid. Ugh. Um, so the force of buoyancy is equal to the density of the fluid times the force of gravity of the crown over the density of the crown times the acceleration due to gravity times the acceleration due to gravity. All right, now that'll cancel and that'll cancel. I can start plugging in some values here. My force of buoyancy is 0.49 equals the density of the fluid, it's water, so that's 1,000 kilograms per meter cubed, times the force of gravity of the crown is the weight of the crown. That was 8.3 newtons over the density of the crown. All right, I'm down to just one variable, so I can just solve. And when I solve, I get that the density of the crown is 17,000 kilograms per meter cubed. Hey, hey, hey. So I successfully have a density of the crown, and then I compare that to the density of the gold, and I see that it is less. So it would appear that the crown is not pure gold. We may have been taken by an unscrupulous goldsmith, or practically like everything made of gold. Gold is too malleable to actually have pure 100% gold. So it's better to mix it with something else so that it can actually hold up as a piece of jewelry. If you gave Archimedes or King Hiero a pure gold crown, it would be too easy to dent and bend. So I think the goldsmith is actually doing good work. Good job, goldsmith, by mixing this gold with something else so that it has a little bit more rigidity and lastingness. If you have like a gold ring or something, it has inevitably something else mixed in with it so that it doesn't change its shape or be able to get dented or pulled off your finger. Cool. Um, so, it's not pure gold, but I think that's probably okay. Yeah, stop being so kingy, King Hero of Syracuse. All right. Um, it's time for float or sink, my favorite part of kindergarten and also AP Physics. So, we can determine whether an object floats or sinks using the force of buoyancy. If an object sinks, that means its weight is greater than the force of buoyancy. Basically, we're just doing the overall balancing of two forces on our free body diagram. If weight is greater than buoyancy, it'll sink. If weight is less than the force of buoyancy, it floats. And if weight is exactly the same as the force of buoyancy, it has neutral buoyancy, and so it can sit in the middle of the water. That's what fish are aiming for. Fish don't want to float to the top, and most of them don't want to sink to the bottom either. They want neutral buoyancy, and they achieve that by having an air bladder inside that allows them to match the density of the water that they're in. So you fish could go into slightly denser or slightly less dense waters, depending on how salty the water is, and still be okay. Although don't take a freshwater fish and put it in salt water or vice versa. They don't like that. Um, okay, so a floating object, if it is floating on the surface, is in static equilibrium. So if it has a density and volume of the object floating on a density of the fluid, it will displace the same amount of liquid as its own weight. So I can do that by noting that since it's in equilibrium, the force of buoyancy is equal to the force of gravity. Then I can turn these forces into masses times acceleration due to gravity, which becomes density times volume times acceleration due to gravity. One side is going to be the fluid, that's the buoyancy side. The other side is going to be the force of gravity, that's the object side. Gravity cancels off of both with my red slashes, and I'm left with the volume of the fluid is equal to the density ratio, density of object over density of fluid, times the volume of the object. They do a little example of this one where they're comparing an iceberg with ice density versus seawater density to show that 89% of the iceberg is in fact underwater. Only 10% of the iceberg is on top, just like all of those inspirational posters about how deep icebergs and also you are. There's so much under the surface. Good job, human beings. Um, Big picture idea here, an object will displace its own weight of water if it is not fully submerged. All right, which has the greater buoyant force? A block of iron sinks to the bottom of a vessel of water, while a block of wood of the same size floats. On which is the buoyant force greater? Okay, this one's actually counterintuitive. Because it feels like the wood would have more buoyant force because it floats. That turns out not to be true. So the block of iron is going to have greater force of buoyancy because the iron is fully underwater. And since it's the same size, the iron will displace its volume. The wood will only displace its mass of water. And since it's floating, it's not displacing its full volume. It's displacing this much water, but it's not displacing that much water. While as iron of the same size, I guess I need the iron of the same size displaces all of its volume. The wood doesn't displace all of its volume, but the iron does. So the iron is displacing greater amounts of liquid, greater amounts of fluid, and thus has a greater force of buoyancy. Okay. So how do boats float? We have big boats that are made of iron and steel and things that don't float naturally. Most boats are not made of wood anymore. So how do we do that? Effectively, the boat holds a whole lot of air on the inside, which makes its average density less than the density of the water. We can also do this with a force of buoyancy. As I'm placing the boat into the water, I always have the same weight of the boat, and it will keep displacing until the total amount of water that it displaces is equal to its weight. And so once oh, that almost looks like a little sailboat. Yay. Not intentional. Sorry. It's supposed to be an arrow. Um, Once it displaces an amount of liquid equal to its weight, it is now floating. And so now it remains in equilibrium. Great. Stop and think. An ice cube is floating in a glass of water that is filled entirely to the brim. When the ice cube melts, the water level will fall, stay the same, or rise, causing the water to spill. With the ice cube, it should stay the same. That's because ice is slightly less dense than water. So I've got a cup of water here. It has an ice cube floating in it, but I just said that 90% of an iceberg is underwater. So this little bit that is above is the 10%, but it's only displacing 90% of it's displacing its whole mass. So when the water goes back in, it will stay at the same level. Now, if the ice was stacked on something else, then it could overflow, like if the ice was on the land. But if it's ice in the water, it will just replace its own level. It's already displacing all of its mass. All right, fluid motion. So, fluid motion. Big idea here is that the same amount of volume passes through a tube. So if I go from a larger tube to a smaller tube, I need to speed up the water so that the same total amount of volume, this is the volume right here versus the volume right here, remains the same. I can represent that by saying the volume, area 1 times the change of position, or area 1 times the velocity, is equal to area 2 times its velocity. So area 1 times the velocity 1 equals area 2 times the velocity 2. I do want to make sure that we now note that this v is velocity as opposed to the volume v, which is capital V. So now these are supposed to be lowercase v's, which I admit is not super clear. But for this equation, they are velocity v's, not volume v's. And that's given again in your physics cheat sheet. All right, let's do an example. Let's see, the speed. No, this isn't an example. This is just another cool thing. The speed of the water is inversely proportional to the diameter of the stream. So if I have a big circle, I don't go as fast, and thus I fall down. If I have a very little circle, I'm going to come out way faster. Because I have a smaller circle, I need the same volume of water traveling out every time period, every second, and so I have to go faster. That's also why we see the water gets narrower as it goes down from the tap. And increasing speed as gravity causes it to fall leads to the diameter of the water shrinking. Kind of cool. Now, we can note this, that the change of volume over time, right, the movement of the water, volume over time, is equal to the area times the volume. If we just double check on units there, volume is in meters cubed per time, which is in seconds, as opposed to area times velocity, that is area in meters squared times meters per second. The units match up. So volume flow rate is constant at all points in a tube. And Q here stands for volume flow rate. How much volume per time or how much area times speed. Same, same. And both are Q, volume flow rate. All right. So speed of water through a hose. A garden hose has an inside diameter of 16 milliliters. The hose can fill a 10-liter bucket in 20 seconds. What is the speed of the water out of the end of the hose? Okay. So it's a volume flow rate. I need the speed of water, and I need to know it fills 10 liters in 20 seconds. So its flow rate, Q, equals 10 liters per 20 seconds. And then it helps to know, sorry, this is a volume over time. That's capital V volume. It helps to know that in a liter are 1,000 cubic centimeters. There's 1,000 milliliters, and a milliliter is equal to a cubic centimeter. So that's 10,000 centimeters cubed in 20 seconds. That means if I divide here, 10,000 divided by 20 is 500 centimeters cubed per second. So then I am trying to figure out the speed of the water out the end of the hose. So basically, I'm going to do volume over time equals area times velocity. I just did volume over time. That was 500 centimeters cubed per second equals the area. It's a circle, so that's going to be pi r squared times the velocity. I'm solving for the velocity. Since I have centimeters cubed, I'm going to put this r in centimeters. So 500 centimeters cubed per second equals 3.14 times 1.6 centimeters squared times V. Solving for V, I get V equals 250 centimeters per second, which is 2.5 meters per second. Yeah. So this one was primarily a flow rate, volume over time equals area times velocity, solve for velocity. I did have to note that, sorry, the area here is the area of a circle, R, and then I needed the whole area. And did I get the R right? Oh no, the inside diameter of 16. So that's the incorrect value. This is why I should actually plug things in and check my work. It's 0.8 centimeters squared. That makes more sense. Okay. So the 0.8 is the radius because the whole thing across is the 1.6. All right. Good checking of work. Oh, last piece. What diameter nozzle would cause the water to exit with a speed 4 times greater than the speed inside the hose? Okay, so to get 4 times greater, um, I need to compare, where was it? AV equals AV, because I'm trying to get a velocity that's 4 times greater. AV equals AV. I want my velocity to get 4 times greater. So area times velocity equals the unknown area times 4v. If I'm going to make that 4v, this had better be 1/4 of the area. So I'm trying to go down to 1/4 of the area. And I know that area is equal to pi r squared, since 1/4 pi r squared, since I need the value in front of r here, it would have to be 1/2 of the radius, because 1/2 squared gives me 1/4. So I'm going to go with half of the radius, and that means half the diameter. My previous diameter was 16 millimeters, so my new diameter has to be 0.8 millimeters. Centimeters. 8 millimeters, 0.8 centimeters. Oh, wake up, Mr. Williams. Come on, man. Get your digits together. Okay. Um, Now we can look at particles in a fluid move along streamlines. So as something is moving, it's going to follow a consistent flow pattern. As I'm running streamlines, streamlines are never going to cross. The fluid particle velocity is going to be tangent to the streamline. So I've got that green arrow. And the speed is going to be higher where the streamlines are closer together based off of that AV equals AV kind of thing. AV, AV. So here the velocity will go down because the area is going up. So the closer the streamlines are, the faster it goes. And here's a little bit of the explanation why. Every fluid particle that makes up the element moves on its own streamline, and as it moves, its shape changes, but the volume remains constant. So the volume here is equal to the volume there. All right, the figure shows volume flow rates in centimeters cubed per second for all but one tube. What is the volume flow rate through the unmarked tube? Is the flow direction in or out? Okay, so in total, I need the same amount of volume flow rate in and out because there's only so much space inside this container, and I'm assuming it's filled with water, liquid, whatever. So I've got 10 in plus 10. I've got 2 in plus 2. I've got 1 in plus 1. So I have a total of 13 coming in. Going out, I've got minus 4 and I've got minus 8. So I have a total of minus 12 going out. That means I have a grand total here of plus 1. So I'm getting plus 1 too many, right? Which means I need to, in order to keep it balanced, lose 1. So I need to have a flow rate of 1 centimeter per second, centimeter cubed per second, and it needs to be going out so that I have 13 in and 13 out to balance. More with this fluid element through tubes. So as a tube narrows, we have the velocity increasing. Now, because the velocity is increasing, we would call that an acceleration. And we know that force is proportional to acceleration, so we have to have a force leading to that increase of speed. And that force would be a pressure, right? We know that's going to be a pressure because it's a force over the area. So I would see some pressure as I go to a narrower tube. I can also measure this using a Venturi tube. Increased pressure versus decreased pressure. Slower moving fluid is going to have higher pressure because the pressure force is force over area. I need to have that acceleration right here, which means I need the force to be right here, which means I'm going to have higher pressure, and I'll see that higher pressure with higher movement, higher heights on my fluids. And here, where the water is going faster, I'll have lower pressure, and I'll see that with the lower heights because it's the force over the area. All right. I can also do this for streamline fluids. So if the streamlines are getting closer together, that's an indication that I have lower pressure. It's going faster. So uh, faster equals lower pressure. And I also see that by closer streamlines. So the faster it goes, the lower the pressure is. This gives us airflow over a wing, creating lift. Over the top, I have faster wind going over the top than on the bottom. So I have lower pressure on the top than the bottom. And so I see a lift force going up like this. This is also why tornadoes can be dangerous for houses. If you get really, really fast wind going across the roof of your house, it can create very low pressure. The house pressure is normal air pressure, and so that creates a pressure up or a force out that could rip the roof off your house. Okay, so this introduces Bernoulli's equation. And oh boy, is this a doozy. This one is given in your physics everything sheet, your physics cheat sheet. Um, but it basically takes a look at two objects. An object in a tube that has a different thickness and a different height and a different pressure. Um, so what we're basically doing is balancing the energy. The pressure would be equivalent to the work. The kinetic energy would be represented by 1/2 density times the velocity of the liquid squared. And then the acceleration due to gravity would be the density times the gravity times the height. So we'd have pressure plus 1/2 density velocity squared plus density gravity height equals the same deal for the second thing. In both of these cases, it's effectively like a balancing of energy, work plus kinetic plus gravitational, just with liquid stuff, with fluids. And we call that Bernoulli's equation. It's in your physics cheat sheet. Let's put it to action. Um, yeah, we're going to do that with this practice problem. Water flows through the pipes as shown. The water's speed through the pipe is 5 meters per second, and a pressure gauge reads 75 kilopascals. What is the reading of the pressure gauge on the upper pipe? Okay. Um, so I have to figure out my setup here. And so for my setup, I am going to do, this looks like I've got my two systems. So I'm going to do pressure plus 1/2 density velocity squared plus density times, I got to check my equation. I haven't memorized this one yet. Density times gravity times height. Okay. Equals the same deal for number two. Pressure plus 1/2 density times velocity squared plus density times gravity times height. Okay. And what I'm trying to figure out is the pressure on two. So I'm solving for pressure on two. I'm going to make that one a different color just so it stands out. The other thing that I don't totally know is the velocity on two, which is going to get a little bit tricky. So I think I first have to figure out the velocity on two because I do have the pressure here. So step number one, I'm going to shift sideways just a little bit and try to figure out what is the velocity on two. To do the velocity on two, I do have the area and the velocity on one, and I've got the area on two, and I need the velocity on two. So I'm going to do area one, velocity one equals area two, velocity two. My area here is going to be pi r squared. Um, so pi times 6 squared times 5 meters per second equals, up here is 4 pi times 4 squared times v2. The pi will cancel from both sides. This gives me 36 times 5. So this is 36 times 5 divided by 16 equals V2. I'll run the math on that, and I find that V2 is 11.25 meters per second. Now, I think I can plug everything else in. I have a pressure of 75 kilopascals. That's going to be, let's see, 75,000 pascals plus 1/2 its density of water. So my density, I'm always going to use 1,000. Oh no. No, I should be fine. Never mind. Okay. Um, plus 1/2 times the density of the water is 1,000 times 5 squared plus 1,000 times, I'm just going to use 10 times y, which is going to be, oh, 0. It's going to start at 0. It's going to go up 2 meters here equals P2 plus 1 half times 1,000 times this one's my 11.25 squared. Ah, can I move this out of the way? Yes. Um, plus 1,000 times 10 times 2 meters in height. Algebra, 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 algebra. And I should get P2 equals 4,600 pascals or 4.6 kilopascals. Nice. All right, I think that worked. Whew, what a relief. Um, Last little bit. One more stop and think. Rank in order from highest to lowest the liquid heights H1 to H4 in tubes 1 to 4. The airflow is from left to right. Okay, so I have an air pump. Right here, there is no overall motion, so I just have atmospheric pressure. So that'd be 1 atmosphere plus no additional pressure from the speed. Then I know, based off of these diagrams, that the wider it is, the greater the pressure, because it requires the down to accelerate. So looking at my diagram, I'm going from here to here. This is going to be the widest, so that's going to be the greatest pressure, which means this should be the lowest. This is going to be the fastest, so it should be the highest. H4 should be in between those two. Oh, the direction of the air pump is the other way. Whoops, sorry. This way. Um, doesn't matter. And then I have this atmospheric pressure that has no speed on it. Um, huh. No speed on it means there's going to be no addition of pressure. So I'm pretty sure the atmospheric one should be the highest, right? Because there's no addition, like slower has greater speed. Or does this zero, you know what? I am going to pause and figure this out. Okay, glad that I paused to figure that one out. Took me a little bit of processing and thinking time. I think I had the right idea. I knew that pressure is going to be greater where um, the speed is faster. And so this has the most speed. So this will be, oh, get the right thing. Uh, this will be my fastest liquid heights. So heights is based on pressure. So it's going to be H2 has the fastest. That's going to be greater than H4, which is greater than H3. And then finally, H1 has no pressure on it, no additional speed. So it's going to be the lowest. That'll be greater than H1. So that no additional pressure means that it has the lowest height. Okay. Whew, one almost caught me. Fortunately, I have the power of the pause button. Last thing that is actually on the AP stuff, and then I'll do a little bonus. Um, Pressure. pushes water sideways out of the holes. So the deeper it is, the greater the force of gravity. We can also think of this like a conservation of energy. The deeper it is, the more potential energy is pushing on it. That turns into kinetic energy. So I could say mgy equals 1/2 mv squared. Um, I could substitute in density times volume for mass, but I'd do that on both cases, and that would cancel. And then if I solve for velocity, I could figure out the velocity of the water coming out of a hole by doing the square root of 2 times the acceleration due to gravity times the depth of the water. This is really familiar from conservation of energy, but I just wanted to highlight that that was possible. You could do a derivation to figure out the speed of the water, just like as if it were on a Hot Wheels ramp, right? If I had like a little Hot Wheels car or a marble, I could do the conservation of energy and figure out the velocity as it left. Same idea. All right, last piece. This is not part of AP exam, but I think it's kind of interesting, so I'm going to throw it in there. I'm intentionally skipping all the problems that are related to this because it's not on the AP Physics 1 exam. But viscosity. So viscosity is thickness or resistance to flow. Very, very thin things, thin's the wrong term. Very, very fluid things are able to flow easily, like air flows really easily. It has a very low viscosity, 1.8 times 10 to the minus fifth. Water has a viscosity around 1 times 10 to the minus third, or 0.001 pascals per second. And then other things can get a lot thicker. Motor oil has a velocity around zero point 0 something, although it can, if it's freezing cold, get all the way up to 30,000. Honey has a viscosity of 600 or 20 if you heat it up enough. So basically, thicker stuff have greater viscosities. Um, then, based off of that viscosity, uh, we've been treating everything like perfect frictionless tubes. But in reality, the tubes are not frictionless. The edges of the tubes have surface to them, and that surface is going to cause friction. So for a viscous fluid, we're treating everything like an ideal fluid. And the reason that we can ignore viscosity is we're going to assume that every AP physics is an ideal fluid. So the velocity at all points will be the same. Nice, easy flow. Practically, in the real world, where it's not magic happy physics land, boo. As the water or the liquid gets close to the edge of the tube, it gets caught on the edge of the tube. It'll go fastest in the middle, the center of the tube, and it will go slowest out on the edges of the tube. We can use this equation to figure out the pressure reduction due to friction. It is a gnarly equation. 8 pi times the viscosity times the length of the tube times the average velocity divided by the cross-sectional area of the tube. And that would tell me how much the pressure will reduce from one part to the other. You could also solve for the average velocity of the thing in the tube using this equation here. That's a derivation of the same thing where I turned area into the r squared piece. And then finally, I could find the flow rate by doing the velocity average times the area, and that would give me that guy. We call this Poisson's equation, which is nice. So, last one, just a fun stop and think. Yay, more fun AP physics. That is my wife trying to call me. She's not going to be happy, but I'm going to finish in like the next minute and call her back. A viscous fluid flows through the pipe shown. The 3 marked segments are of equal length, across which segment is the pressure difference the greatest. Okay, so the pressure difference is viscosity is constant, 8 pi is constant, L over A, all of these seem to have the same lengths. Yep, they all have the same lengths. So the L stops mattering. So I'm left with the change of pressure is equal to the velocity average over the cross-sectional area. B is going to have the largest cross-sectional area and the slowest velocity. So this is big and this is small, which means it won't be affected very much, right? A small number, 1, over a big number, 100, means not very much change of pressure. So the one that's going to have the greatest pressure difference would be A, because it is going to have fast moving liquid and it has a small cross-sectional area. So I've got a big number over a small number. It's like 100 over 1, and that's going to be a big pressure difference. So in order, it would be A would be the greatest, which is bigger than C, which is bigger than B. Okay, and that's based off of that equation here, where I kept 8 the same, pi the same, viscosity the same, and L the same, so that the only differences were the V and the A. All right, that, my friends, is chapter 13. You have done it. If the AP Physics curriculum is still the same, that's the end of the course. You did it. Last video. Great job.